Welcome back. In our last lesson, we talked about the different ways that we can define waves and refer to waves using a common vocabulary. So things like amplitude and wavelength, crest or trough, compression, rarefaction. Today, we're going to talk a little bit more about how we can describe these waves, but also relate these variables together using some mathematical relationships. So ultimately, our goal today is to focus on the mathematics or the calculations that go around waves. Now, to start us off, let's review a little bit two main terms, two big categories that we talked about in the last video. I have two different types of waves here presented on the screen, A and B. I would like you to think to yourself, how would we define these? One is transverse and one is longitudinal, but which is which? If you remember back to our conversation, transverse wave, the hint that we gave you is T is like an upside down perpendicular sign. A transverse wave is a wave that the particles vibrate perpendicularly to the direction of the wave's travel. So B here is a transverse wave, and a longitudinal wave is when the particles vibrate parallel to the direction that the motion is going. So we'll see a longitudinal wave propagate in these kind of compression waves, so high areas of high pressure that travel along, whereas a transverse wave is a wave that goes up and down as it moves sideways. Now we can also talk about these waves in terms of energy, just based on the properties that we've already discussed. One property we discussed was amplitude, or how far a wave gets from its center point. The larger the amplitude is, the more energy that wave is carrying. So in terms of sound, that high amplitude wave is a louder sound, or a low amplitude wave carrying less energy is going to be a softer sound. In terms of light, a bright light has a high amplitude, high energy, and a dim light has a low amplitude, low energy. That kind of makes sense. Now, another thing that you can kind of figure out common sense is how the wavelength affects the energy. If you stretch out the wavelength and make the length really long, you're going to experience less waves in a given amount of time. And that higher wavelength results in a lower energy. A lower wavelength then means you're squishing a lot of waves into a smaller space and then increasing the overall energy of that wave. We can time this wave and talk about how the wave is occurring in units of time and then ultimately for our frequency. So one way that we can time a wave is to count how long it takes in between crests or troughs or identical parts of the wave. We call this the period. So the period is the time per cycle. And period actually shows up other places in physics as well. But here we're going to refer to period with the symbol of a capital T. T stands for time. Lowercase t will just be a generic time. But a capital T is the time it takes for one wave exactly. And since it's the time, we're going to measure time, period, in seconds. So if I said that this wave has a period of 2 seconds, it means that the wave goes 1 1,000, 2 1,000, and comes back to where it started in that 2-second span. Frequency is also important. This is very closely related to period, which we'll see in a second. But frequency is the cycles per second, is how many waves have happened in a given amount of time. Now, the unit that we are going to, or the symbol that we'll use for frequency is this italic lowercase f. And then our unit is a unit known as hertz, abbreviated Hz. Hertz basically just means how many cycles per second. So, for instance, a common sound might have a frequency of like 526 hertz. That means that there's 526 vibrations back and forth every second. So typically frequency is going to be really, really useful when we're defining sound and light because the number of cycles per second is a lot, but the time for each individual cycle is very, very small. These are related to each other by a very simple relationship. We say that the frequency is just the reciprocal or the inverse of the period. The way we write that mathematically is we say that the frequency is 1 divided by the period. In terms of symbols, we say that f is 1 divided by t, or we could rearrange this if we wanted to multiply both sides by t and divide both sides by f, so we get t is just 1 over f. And both of these are just rewrites of the exact same relationship. And depending on what you're looking for, you can use one or the other. So to give you an example of this, Taylor Swift's song Shake It Off has a tempo of about 160 beats per minute. So translated down to hertz, or beats per second, it means it's a little over, somewhere between 2 and 3 beats every second. So we'll specifically say 2.67 hertz, that many beats per second. I would like to know how many seconds are in between each beat. This is just another way of saying the period. So what we're given actually in this case is the frequency. Hertz is a unit for frequency, so we say the frequency is 2.67 hertz. What we're trying to find is the period, capital T. Our relationship of these two that can help us find period is this one right here, that the period is 1 divided by the frequency. So my equation that I'll use is T is equal to 1 over F. Plugging in what I know for F, my equation goes to 1 divided by 2.67. Plugging that into my calculator, I get a period of 0.37 seconds. So what this means in terms of our example is if you were like snapping along to Taylor Swift's Shake It Off, which you have to do because it's just so catchy, you would have 0.37 seconds in between each snap. That's how long it takes for one beat to happen. I would like you to try this next one on your own. So you're standing on the beach with your feet in the water and you notice that a new wave comes crashing in every 4 seconds. I would like you to calculate the frequency of these waves. For your reference, the 2 different equations that we talked about are up here. So grab a piece of paper, grab a calculator, plug this out, and I'd like you to solve for what is the frequency of these waves. All right, hopefully you've had a chance to try that. If not, you can pause the video and try on your own. What we are given here, 4 seconds, is actually the period. That's the time for one complete wave. So I'm going to list that out. T is equal to 4 seconds. I'm trying to find the frequency, which means I'm going to use this equation here. F is equal to 1 over T. Plugging in that period, 4 seconds for T, we get 1 divided by 4, which is 0.25 hertz. That means that we experience a quarter of a wave every second if it takes 4 seconds for a complete wave. Now, an example that's a little bit more involved is one shown right here. You're pushing your younger brother on a swing. You end up pushing 12 times in 1 minute. What's the period and frequency of the swing? And the tricky part here is that 12 is not the period and it's not the frequency. You can't just say that that number, just because you're given that one, is one of these important variables. Instead, you have to figure out, okay, what does that 12 actually tell us? We know that 1 minute is the same as 60 seconds. So from that, if I know that it takes 60 seconds to push 12 times, it'd be pretty easy actually to figure out how many seconds for every one push. That if I took that 60 seconds 12 times, I can find that it's 5 seconds per push. Now down below here, what showed up a little bit early, is if I then took that 5 seconds and did 1 over period, I would find that the frequency is 0.2. So it's possible that you might see an example that is providing you a number that isn't actually one of the numbers that you need, but can be helpful to find either the period or the frequency. And once you know one, you can easily calculate the other. Now, wavelength and frequency are very closely related. That if you have a long wavelength and that wave is traveling past you, it means you're not going to experience as many waves in a given amount of time. So a longer wavelength ultimately results in a lower frequency, which means a shorter wavelength, if the wave is really short, it means you're going to experience waves traveling a lot fast, or not necessarily traveling faster, but you're going to experience more of them per second, which means you're going to have a higher frequency. So this can be related then in a mathematical equation, all leading back to the speed of that wave. We said that the speed is equal to the frequency times the wavelength, which means that if the speed stays constant and the frequency increases, then the wavelength has to go down and vice versa. So the way we're going to represent this in symbols is speed is represented with a V, just like we did when we talked about speed and velocity. Now the units of speed are still going to be meters per second. Frequency we represent with this italicized lowercase f, and that is represented again in hertz. And then wavelength, which we saw last video, is represented using this lambda symbol, this Greek letter, and wavelength is represented with a lowercase m for meters in its units. Here, if you're trying to make the units agree, You need to know that hertz is actually a rewrite. It's a derived unit that represents 1 divided by seconds. So if you multiply those together, you would get meters per second. But what you need to know is this equation, v is equal to f lambda. Speed is frequency times wavelength. And how that can help us is by solving some of these problems. If you're given 2 of the 3, you can always find the third. A piano string vibrates with a frequency of 262 hertz. Frequency is 262. If these sound waves have a wavelength of 1.3 meters, what is the speed of sound? The equation that we were given is this one right here. Speed of sound is just frequency times wavelength. If we plug in those values, 262 hertz times 1.3 meters, we get a velocity, a wave speed of 340.6 meters per second. When we talk about sound a little bit later on in this unit and the speed of sound, you'll see that that is really close to the speed of sound in room temperature air. Another example here is light. When we talk about light later on, you're going to see that the numbers are either really, really big or really, really small, which means we are often going to be using scientific notation for some of our light calculations. Speed of light is about 300 million meters per second, or 3.0 times 10 to the 8th meters per second. Green light has a wavelength of 5 times 10 to the negative 7th meters per second. So the light is really, really fast, but the wavelength is really, really tiny. I would like to know its frequency. I can list out my variables. The velocity and the wavelength are there, and I want to find the frequency. Now, this is that base wave speed equation, but I can rewrite that to solve for frequency. I just divide both sides by lambda. To get frequency is just the wave speed divided by the wavelength, v over lambda. I know what v is, I know what lambda is, and I can plug that in. Now here's the hardest part. Plugging this in on your calculator is kind of tricky. When you do that, you need to really be careful about how you're using exponents and how you are dividing. So 2 things that you can do. One is you could use that E key, there's a capital E key on your calculator in the place of times 10 to the power of, or you can make sure that you use parentheses around both of these terms. With that in mind, go ahead and try it on your calculator. Pause the video and see what you get to see if it compares to what I have calculated. Okay, if you plug this out, you're going to find that the frequency is really, really big. Really, really big. It should be times 10 to the 14th. You'll get 6 times 10 to the 14th hertz, which means that green light, as your eyes are experienced, actually accounts for 6 times 10 to the 14th vibrations every second as it enters your eye. All right, the final piece that I want to talk about here is how you can read a wave and get some of these properties from a wave drawing. Now this wave drawing looks different than the wave drawings we saw before. In this case, our x-axis isn't distance, it's actually time. So I can actually read the time it takes for this wave to go one complete wave. Now first, I want to count the number of waves. I go from here all the way up and all the way back. That is 1 wave. Then I have 2 waves. Then I have 3 waves. So the number of waves here is 3. Now the period of this wave is the time in between crests or time in between troughs. And I see it goes from 4 to 8. So the period of this wave is 4 seconds. That's how long it takes for one full wave to complete. The amplitude is how far you are away from the center line. So the amplitude here is 2 meters. And then the frequency can't be read directly from this drawing. Instead, we have to use this equation. Frequency is 1 divided by the period, and the period is 4 seconds. So 1 divided by 4 gives us a frequency of 0.25 hertz. With this in mind, just another quick example. The number of waves here goes up and back down. That is 1, and then another half. We get 1.5 waves. The period here, think to yourself what that might be based on this drawing. Period, as you can see, is 0 to 8 for one complete wave, so the period is 8 seconds. The amplitude is 3 meters, and the frequency, 1 divided by 8, is 0.125 hertz. So from that, you should be able to calculate these properties of the wave.